Okay, yeah, apologies for that. Yeah, so I am virtual. Unfortunately, I wasn't able to join you guys in person today, but through the power of the internet, I can at least deliver my talk this way. Am I okay to start, or can you see the slides okay?
Right.
Excellent. Okay, yeah, thank you for having me. As I say, sorry I couldn't be there in person. So initially today, I was planning to talk about the abundance and distribution of volatiles in nominally anhydrous minerals by atom probe tomography, which sounds very fun and very challenging, and it turns out it is. So we haven't been able to do too much with abundances, but we're at least going to show some cool atom probe data. The implications for volatile reservoirs and the lunar regolith are still very much there, though. So backtracking a little bit from actually putting pure numbers on this, but still going to show some really, really fun stuff from a technique that a lot of people haven't really been exposed to, especially in the lunar science community. So the bulk of what I'll be talking about today revolves around space weathering. So it's been a very interesting session. Previously, I was subscribing to the idea that hydrogen kind of comes in and you magically get water. So it's been quite eye-opening to really think about the mechanisms that are defining that. So when we think about space weathering, at least in the lunar regolith, think about the idea of micrometeorite impacts, solar wind implantation, and all those kind of really, really complex mechanisms that are going on in that superficial layer. Obviously, in reality, it's not just happening to the very surface. We're getting impact gardening and this sort of regolith being churned over and over. So these effects, for example, hydrogen implantation, could be occurring at deeper intervals, sort of after that cycling process. But I think the main point from all this is that the mechanisms are still fairly poorly constrained. So we know there's a lot going on without an atmosphere, without any protective buffer there. The lunar regolith being exposed to all of this for its sort of geological history. We know a little bit about the kind of products that are produced from space weathering, so nanophase iron in particular. There's a nice study coming out of the Tanger 5 samples back last year, actually starting to constrain how and why nanophase iron might be forming in different minerals in the regolith. And obviously OH formation, which we've already heard quite a bit about today, OH and H2O formation. The mechanisms are still fairly poorly constrained, and that is because these interactions are occurring at such a small scale, they're pretty damn hard to visualize and interpret. So my background is very much in geochronology, so I like to date rocks, and that involves understanding the structure and the petrology of the samples. So I very much subscribe to the idea of correlative microscopy, so linking sort of length scales here across time and space, right? So you look at your whole rock sample, even better with things like the Apollo samples, because you know exactly where on the moon they're coming from, as opposed to a meteorite, where, you know, pick your poison. Start with your whole rock, come down to thin section, correlating the whole way. And now with modern techniques, we get, such as SEM in the EDS work now, we can go down to the mineral scale, go down even further using something like TEM, and you can actually image the crystal lattice. And now, through the power of atom probe, we can actually start to image atoms in 3D. So you get to produce beautiful videos like this. This is from the Tagish Lake carbonaceous chondrite, but you can imagine this is sodium decorating a subgrain boundary within that sort of magnetite framboid in the sample. What is atom probe? It's a fairly new technique for us in the geological and planetary sciences, but for material sciences, this has been kicking around for about 50 years now. The biggest hindrance for us in particular is sample preparation. So historically, atom probe we used to analyze metals and conductive samples. Obviously, rocks aren't particularly conductive, but through the advent of the laser, the laser atom probe, we can actually now start to look at the sort of materials that we care about. Sample preparation is the big thing. So you need a focused ion beam, SEM. So the samples are prepared. You have your thin section or your grain mount or your sample cut around the area of interest. So if I can just use, hopefully you guys can see that. You can isolate the grain of interest under a platinum cut. You cut it out, so you completely isolate it in 3D. Lift it out using a micro manipulator, same way you would a TEM lamella. And then you go along, you stick it on these little silicon posts, cut it off so that it's completely isolated in 3D. And then you just operate your focused ion beam in a circular annular mill to produce this lovely little fingertip shape, which is the final specimen. So the reason we need it to be that shape is because once it goes into the atom probe, it's super cooled down to about 50 Kelvin, and then it's exposed to a rapid laser pulse. It operates about 100,000 hertz. And that energy is then transported to the end of the tip, where it's coupled with a field evaporated ion sort of electrode and a position sensitive detector. So the reason this is so cool, this time of flight detector, is that we know if an atom breaks off the top of the tip, it will land on the top of the detector, from the bottom of the tip to the bottom of the detector, and then the first laser pulse will evaporate the front of the tip, the last will evaporate the back. And that means that we get the X, the Y, and the Z coordinate, which allows us to do those really nifty 3D reconstructions. And like I say, it's coupled with a time of flight mass spectrometer, from flight detector, sorry. And that allows us to measure the whole mass to charge state ratio spectrum at once, basically. So you can measure everything from your hydrogen down at 1 Dalton, all the way up, I mean, not because you're on here, but sort of like uranium 238. If it's there, we'd start to see a peak. So you don't have to select what species you want to measure, you just kind of get the whole grab bag, right? So minimally destructive, we're only cutting out, I mean, the example here is sort of like 10 by about 30 micron square. And then we're getting quite a high scientific yield from that extraction. In terms of space weathering, Atom Probe is starting to really sort of show its face, which is really exciting, at least for me. So there was a study last year by Luke Bailey looking at some of the returned Hayabusa 2 grains. So in olefin, they actually managed to image OH enrichment and H2O enrichment in the outer kind of 30 nanometers or so of the grain. So what they've done here is like a chromium cap, so you know exactly where the surface of your grain is, and then everything below that they can be confident is sort of the nanometer scale interaction of that grain. So they've actually imaged H2O here in the outer layer. So they improved confidence in that by actually doping from terrestrial standards, and then they get very different profiles of enrichment. So they're confident that this is from space weathering and not for sample preparation or sample matching. On the moon, Jenica Greer back in 2020 actually looked at atom of ilmenite. So the same idea, you put in this case, they use platinum as a capping layer. Just so you can be confident you're getting that very outer superficial layer. And they actually managed to image microphase and nanophase iron, and they even managed to grab a few vesicles, which are really challenging by Atom Probe unless you supercool your sample throughout. And then unfortunately this was only in an abstract, but Josiah Lewis back in 2019 actually had a look at some of the agglutinates from the Apollo 11 return samples, and again they managed to get nanophase iron, from which they found nickel, so it's a meteoritic component. And they also managed to try and infer some growth mechanisms within those regoliths. So they've got iron sulfur grains embedded in iron, which they inferred to form from Oswald ripening. So Atom Probe is already starting to show a way that you can visualize these nanoscale space weathering features and actually try and interpret the formation mechanisms as you go along the way. For this study, we kind of wanted to broaden the range of minerals and samples that have been looked at. So the only olivine study previously was in the Hayabusa 2 grains, so fairly young soils. So we had a look at soil 6500. So it's a very mature soil, at least in terms of the kind of the maturity scale. Primarily an orthosite, as expected, but yeah, about 30% impact melt, and then you've also got a mare component. There is olivine in there. And notably, it's also enriched in meteoritic cinephile elements. So we used EDS on a few of the grains just to target our areas of interest. Went in with 5 Atom Probes using our ion beam extraction method. 2 of them blew up, which is quite a good ratio actually for Atom Probe if you really get into it. But the 3 other tips ran really well, so that's great. We also had a look at a DR5 standard. So this is just a known nanosim standard used here at the Open University. And we just, using exactly the same method, we put a chromium capping layer on, we extracted the tip, and then we just try to measure kind of what's happening at that superficial layer. The main takeaway from this is that OH, here in this kind of tealy color, is fairly homogeneous throughout the sample, and then once you get towards that superficial layer, marked here by this little line, it drops off. So, weirdly, sodium's enriched. I mean, that's some kind of atmospheric interaction, but there's no notable OH sort of enrichment from atmospheric contamination. Quantifying this, as I say, was an absolute nightmare, hence dropping the quantification aspect. Initially, we were getting about 2.9 atomic percent hydrogen when it should be about 0.05. A lot of that was coming from these really weird 1 and 2 Dalton peaks, the pure hydrogen and deuterium. A lot of that will just be noise in the Atom Probe vacuum chamber. So still, we can be confident that this is a real relative distribution within that sample. So we can use this relative distribution, even if not for hard numbers. Diving into the Apollo stuff, so here we've got one of the microtips. The notable thing is that we found nanophase form iron formation right down to about 450 nanometers depth. So really deep. I mean, you can almost call it microphase, but they're still sort of 20 to 30 nanometers. But we do get OH enrichment. So again, you think about what we saw in the terrestrial standard, that OH curve should drop off. We do see enrichment. So that's suggesting, and same as the Hayabusa study, that this is a real kind of space weathering artifact. But the notable thing is that it seems to be decoupled from the depth of nanophase ion formation. So we've got up to about 150 nanometers depth of OH formation within that sample, but nanophase ion going all the way down to 450 nanometers. And there was no meteoritic component in any of the nanophase ion here. The next tip we looked at was completely different. So nanophase ion was very localized, just within sort of 20 to 50 nanometers below that surface. And in this case, it does correlate with OH. So again, you get this little uptick of OH right at the sample surface, which is about the same depth, up to about 100 nanometers. But importantly, we do actually find nickel within these nanophase ions. So it's almost camosite composition, and that's kind of suggestive of a meteoritic origin for these nanophase ion grains in particular. The final sample that ran really well looks a lot more similar to that very first tip, right? So we got really nanophase ion formation and a pretty substantial OH enrichment at the surface again. And again, slightly decoupled. So the nanophase ion, microphase ion, whatever you want to call it, occurs at much greater depth than the OH enrichment. So within those three tips, you've got decoupling of nanophase ion and OH formation, all kind of running in parallel. That's kind of speaking about multiple mechanisms that are potentially forming these things. So I'm very much not a space weathering expert, so take all of this with a grain of salt, but at least interpreting the atom probe data that we've got, the fact that we're getting comparable depths of OH formation in the really mature Apollo 6500 soils compared to the Hayabusa 2 grains suggests that it's more the saturation point of the mineral that stops hydrogen implantation rather than like a time limit factor. So it doesn't matter, we don't need really mature soils to necessarily have deep OH formation. And that's really important for ISRU purposes. So if we're thinking about hydrogen extraction, we don't need to sort of exclude certain soils that might be younger from the maturity index. And finally, thinking about nanophase ion. So again, going back to in situ resource utilization, nanophase ion has often been suggested as a potential proxy for OH formation. So if there's lots of nanophase ion, that suggests there could be quite a substantial reservoir of OH formation, again, tying into this kind of maturity idea. But what we're seeing is that can often be decoupled. So a lot of nanophase ion doesn't necessarily facilitate a lot of OH. And the fact that we're seeing sort of nickel and chromium kind of compositions, camosite compositions, starts to think about different mechanisms for the formation of those grains. So I know it kind of correlates with that kind of impact map that we saw for micrometeorites earlier. Just a few kind of whistle-stop ideas there from the atom probe. I guess the thing I do want to flag up for atom probe before I finish is that, like I say, you get the whole mass to charge spectrum. So you don't have to cherry pick any particular regions of interest in that mass spec. So even though here we've used it to isolate nanophase ion, look at OH and sort of things like that, you can measure uranium, lead, you can measure fluorine isotopes, but whatever you want, right? You get the lot. So it's really useful. It's minimally destructive, at least on the kind of scale that we normally think of with planetary science. And I think it's really going to be the kind of next frontier of sample return analysis. So, thank you.